Howdy folks, Iowegian here. I'm going to do something just a bit different today. As some of you may know, I'm an engineer and like that kind of stuff. I'm a chemical engineer, and so I like problems like this, and sometimes I find unique ways to solve problems that I thought could possibly be helpful to other people. I guess for this to make sense, you probably need to be an engineer, or at least somebody that understands some calculus. And I don't know if I don't have much of an audience as it is anyway. I don't know if any people that watch any of my videos have a technical background, but anyway, I'll just get started, and heck, if nobody watches this, that's okay with me. Alright, so being a chemical engineer, a lot of times I do process calculations that involve mass and energy balances, either steady state or unsteady state. That is, either they don't vary with time, the process variables, or they do vary with time. This here is just a fairly straightforward unsteady state or transient problem, and what I'm doing is an energy balance on a water heater. Get the camera set up here. Okay. You know, like an industrial water heater, where you would have a heating tank providing hot water in a circulated loop, and it would be used to run through a heating jacket or something like that to heat up another process or another device, and generally that's a pumped closed loop circuit. So we supply heated water at a certain temperature. It gives up its heat to whatever the load is, and it is returned back to the water heater at a lower temperature. Okay, and then the heating coil provides the makeup heat to return the energy to the fluid. In this case, I'm assuming it's water. I'm calling it a water heater, but a lot of times they use other types of fluids for this too. Okay, so I've kind of laid the problem out here, and I'll show you how I solve it by hand. There's other ways to solve it too, but so again, this is a water heater energy balance. So I have a heating tank with a coil. Here are my variables. So I've got my supply line and my return line. For each of these two streams, the return and the supply, I've got Q dot, that's volumetric flow, like gallons per minute. T for temperature. The rho stands for density, and C sub P is heat capacity. Now I've labeled each stream with, I'm calling the return line stream 1, so I've got Q1, T1, etc. And and then for the supply line, I'm calling that stream 2, so I've put number 2 subscripts on those variables. I pointed to the wrong thing. This here refers to what's in the tank, so no subscripts, it's just volume, temperature, heat capacity, density. Okay, so what's the objective when you perform a balance like this? You want to derive a general relationship so that you can determine T2 as a function of all the other variables and of time. For this case, I'm going to make the following assumptions. The water heater tank is well mixed, and what that does is, that assumption leads to the properties on the output of the tank being equal to what's in the tank. So in other words, T2 coming out is equal to T in the tank, and similarly for the heat capacity and density. So it's well mixed inside the tank, so what comes out of the tank has the same properties of what's in the tank. It's not technically true all the time. Most process vessels, you actually put mixers in them to make that true, but you mix it for other reasons too. But considering that if you have a relatively high flow rate and a relatively small heating tank, it's going to be pretty well mixed in there. Okay, somewhat related is I'm just going to assume that the heat capacity and density for all streams are equal, even though they're at different temperatures. But I guess the real assumption here is the temperature doesn't vary that much across the water heater. And so I'm just going to call them generally CP prime and rho prime. I'm assuming here steady state flow. That means that the Q1 and Q2 do not vary, and they're equal. And so I'll just call it Q dot. The dot basically means a rate of flow. So, Q dot means gallons per some unit of time, gallons per minute, for example. Okay, and then the last thing is, well, it's not the last, the initial condition at time 0, the temperature in the tank is going to be some initial value, okay? And then I forgot little number 6 over here, no heat losses from the tank. That's reasonable because you can insulate a tank and prevent heat losses. Okay, so the first step here would be to do a mass balance. Well, as I note here, it's trivial because I already said it's steady state flow. So mass in equals mass out. It's pretty much nothing you can do with that. Okay. All right, now moving on. This is the part I'll try to do live here. So page 2. I've got some notes I'm going by. Okay, kind of hard to juggle all this stuff. Okay, now next step is an energy balance. Okay. So when you do a either mass, energy, or whatever balance, it's in equals out plus accumulation, okay? I'm going to get a better pen, so hang on here. Okay. All right, this one seems to work a little bit better. All right, using the variables on page 1, then, in an energy balance for a stream, basically you want mass flow times heat capacity times temperature. Okay, well, I started out this problem talking about volumetric flows, so if you take the density times the volumetric flow, that's mass flow. So gallons per minute times pounds per gallon is pounds per minute. So that's mass. And then T1, because this is my return stream or stream 1. And again, the properties rho and CP, they have a prime on them because I'm assuming they're the same throughout the whole system. Okay, so that's my stream 1 in, and then I'm also adding heat in the coil, Q dot. So those are my in terms, equals rho prime Q dot CP prime T. Now that's really T2, but I said before that it's well mixed, so T2 is approximated by T, plus my accumulation, which you can write this way. It's basically mass times heat capacity times dt. Okay, so you can rewrite this by rearranging it. Same equation, just do a little algebra. And that's my differential equation. You'll note that the variable t, which is technically T of t appears on the left-hand side of the equation in the derivative, and then the second term, and then all of the things are on the left-hand side. And the initial condition, or IC, is at time equals 0, t equals t0, some initial amount value. Okay, so really this whole thing I'm going to call equation 1. So it's the differential equation along with the initial condition. All right, the reason I put it in this form is it's in this general form, which I'm going to use more general variables here. Okay, so if you look at it, those two things are really the same form, only now x is my variable. Okay, with an IC, of course, at t equals 0, x equals x0. All right, this form here is amenable to an integrating factor solution, okay, which is the point of this video. With computers nowadays and all kinds of smart people walking around, we can solve an equation like this on a computer pretty easily, either with a program or with a spreadsheet. I always found it kind of fascinating to solve these things by hand and then do a numerical analysis and then compare the two results, which is what I'll probably do in a later video. But so given this form of a differential equation, you can do perform the general integrating factor approach to solution. And the way that works is you define a variable mu, which is the integrating factor, and that's defined as e to the integral p of t dt. So that's my integrating factor. Then the solution is x of t equals integral of q of t times the integrating factor dt plus a constant of integration divided by the integrating factor. Okay, so I'm going to call this whole mess 2. That's my general integrating factor solution. Okay, so basically I'll be able to take equation 1, define p and q for this case, define the integrating factor in terms of p, and then plug it all in here, and I should have a solution for t of t. All right, so in this case, p of t equals q dot over v. And note that it's not really a function of time in this case, because we have assumed constant flow q dot and the volume of our heating tank is constant. But that's okay, it just makes it easier, right? Q of t, and that's not q dot, that's my integrating factor q, works out to q dot Cp prime rho prime v plus flow over volume times T1. That's also constant. Now, the way I got this was simply by inspection. I put my original equation here in the same form as this one, and you can just stare at it and identify what P and Q are. Okay, so now my integrating factor is E of the integral of Q over V dt, and my Q is constant, so Q over V is constant. I guess I already said that up here. My P is constant, so that integration is very easy, and so that equals e to the q dot t over v. The next thing I need up here is this little piece here, which is integral of q times mu dt. Alright, so if you plug in what I've defined above as P and Q, this works out to Q dot over CP prime rho prime V plus Q dot over V times T1 E to the Q dot T over V dt. Okay, now this you integrate. Great. Okay, I was rudely interrupted with a phone call. I'm sorry. I'll go back over what I just did. I defined the integrating factor approach variables P and Q with respect to our current problem. P and Q I've written out here. My integrating factor is e to the integral Q over V, which my Q over V term is constant, and so that's my result of the integration. Then the integral of Q times mu dt works out to this expression, which we now need to integrate. And I was saying that the integral of, I'll just write it down, the integral of e to the at dt equals 1 over a e to the at, okay? So keep that in mind. That's all you have to do for this integration. And you end up with integral of q times mu equals q dot over c prime cp prime rho prime v plus t1 times e to the q dot t over v. Okay, so now I've got both my terms I need for the integrating factor approach, P and Q, defined in terms of our current problem variables. Okay, so now basically what we have to do on our third and final page is plug this stuff all in. So looking back just a minute, in equation 2, now that I have all these terms written out in terms of our problem variables, and I'll just plug them into this equation and get an equation for our outlet temperature. So from equation 2, T of T equals Q dot over CP prime rho prime V plus T1 times our exponential term plus that integration constant over the same exponential term. Okay, or you could rewrite this as calling that equation 3, and this is more familiar if you do a lot of thermal calculations. Here you've got the decaying term, the negative exponent. Okay, that's a pretty easy equation, and that was actually a pretty quick solution. Only problem is we don't know what this is. So what we do is we use our initial condition, which is T of 0 equals T0. So what I'm trying to say is that's at T equals 0. Okay, so you can take that initial condition and plug it into this equation and determine C. Okay, so if you do that, equation 3 becomes T0 equals, and then this annoying term again, plus C, and then e to the minus qt over v equals e to the 0, because t equals 0, right? So this term goes to 1.0, and that leaves C equals T0 minus T1 minus Q dot over C prime, CP prime rho prime V. Now if we plug this into 3, okay, take this C, plug it into there, then the result is it's a Q dot plus T1 plus T0 minus T1 and that's equation 4, and that's our solution. Okay, so now if you wanted to apply this to a real life problem, you can plug in all of your variables and run this equation out in a spreadsheet, for example, and get the temperature at the outlet of the tank as a function of time. I think what I'll probably do is come up with a realistic problem in a later video and solve this analytic expression, but then I'm also going to take the original differential equation, equation 1 here, and solve that numerically, and then I'll compare the results. That's always fun to do. And like I said, I do this for a living, and I'm getting old and I don't trust myself sometimes, so I always like to have two ways to solve a problem so I can compare the answers.